All right, so here we are with the formal lesson on odds and expectation. Odds are different than probabilities. Odds are ratios. And if you look over here on that one right there, it's what we call 1 to 2. Now there are 2 red. So 2 red, 2 red, 2 blue. I'm sorry, 4 blue. So that reduces to, so this proportion reduces to 1 to 2. Because what we want to show is that absolute proportion in its basic state. We want to make sure that it's simplified. And probability-wise, so the probability of red is equal to 2 over 6 total, which is 1/3. So that's what that comes from. That's what that is, the other 1/3. So notice that the numerator represents the proportion of reds, and then the denominator is overall how many. So for every 1 red marble in there, there's 2 blue marbles. So 2 kinds of odds: odds against and odds in favor. Odds against is generally the proportion of probability of failure to probability of success. What ends up happening, because the denominators are the same with those two, when you simplify it, that's how you just end up with the numerators. Odds against is B to A. Odds in favor is A to B. Odds in favor is A to B. Odds against is B to A. And generally, you put them with a colon. The way you read that is A to B. So the colon kind of reads as the word 2. So sometimes people will write it like that. 8 TO1. And as I said, 2, sometimes people write it as fractions. So these things are just the mirror image of one another. A to B, B to A. If you were to hold that in the mirror, they'll be backwards. All right. So let's see if we can just handle some of these things here. I got problems here that I've worked through before, so I'm familiar with these. And these will go, and I can do the work here to show you. The probability of a horse winning a race is 1/12. So let's say I put that. Probability of a win is equal to 1/2. 1/12. All right. Now, to get the probability of losing or not winning, so here's the key to doing these without having to use the complement rule, but you're still doing the same thing. 1 from 12 is what? 12 take away 1 is?
11.
So then your probability of losing is 11/12. We need both the probability the two complements of one another, the win and the not win, the win and the lose. And you'll notice that in the numerator, 1 plus 11 gives us 12, and that's what we want. That's how we know we've got the complement, if those two add up to be 1. Or to be the denominator, which then, if 12 over 12 gives you 1. All right, so this right here, not the denominator, just the numerator, is our A. And the numerator here is our B. Okay? And we want odds against. So what we're going to do is just write them as such. And that's usually how gambling odds are. If you go to the track, you see a lot of those, they have the big number first, but the big number is the number of losses out of the total of 11 and 1. So out of 12 run-ins of that race, you can expect that horse to win 1 time and lose 11 times. Okay? Any questions about that? All right. All right. Now, let's look at this next one. All right. If the probability of getting an A is 3/13, and then the probability of no A is going to be the complement. What would the complement be? 3 from 13, subtract 3 from 13, that gives us 10. All right. And we know those are complements to one another because 3 over 13 plus 10 over 13 is 13 over 13, which is 1. And that's what complements should add up to be. All right. So essentially what we're doing here is we're using the poor man's complement rule to just subtract 3 from 13 to give us the numerator, or our B. Same thing here. This is the A now. And then this is the B. So odds in favor now. We got them, they're backwards from what was up there. It's A to B. A to B. All right. So that means then odds in favor of an A is 3 to 10. And the odds in favor, as I said, is it gives the number of possible wins out of the total of 3 and 10. So when you do odds in favor, it's a more direct way of looking at it than the odds against. But as I said, is my idea on why odds against is what's used in gambling is because if you got that big number, 11 to 1, it just sounds nicer than 1 to 11. Sounds like you got a better shot. But anyway. And like I said, yes, there's nothing to them. The odds favor and odds against, they're just turned around, mirror image. All right, let's see what else we can do. The next thing is what I call reconstitution of probability from the odds. Well, hopefully we've kind of noticed by now that the two numbers, A to B, if we add them up, they give us our denominator. They give us our denominator of the original probabilities. Okay. So, oh, I'll tell you what, let's just do this last one. Like I said, we got plenty of time here. So let's do another with odds in favor and odds against. This is something we got to figure out the probability is by looking at that deck of cards. So, 52 card deck, you're going to draw one, find the odds in favor of getting an ace. Well, we need to have the probability of an ace. And the ace is 4 over 52. Or simplified, it's one ace out of 13 cards. Because 12 of them are 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, King, Queen, and King. And only one of them's the ace, because the ace and all the other cards make up the 13. So, probability of no ace. Well, again, 1 from 13 gives us 12. So 12 out of the 13 cards are not aces. This is our A, and this is our B. Notice that the A is the numerator of the probability of success, or in this case, the probability of getting the ace. The probability then of hold on a second. So odds in favor is A to B. Okay, so here, odds in favor, A to B. Let's see, I'm going to pencil it in there. This is A to B that we want. So for this answer, it's just going to be 1 to 12. This one is B to A. So this is so what do the odds mean? It's just, well, what is it? What's the whole point of odds? The odds just tells us the ratio of losses to wins or wins to losses. In the case of odds in favor, it's wins to losses. One win for every 12 losses. And 1 in 12 makes up 13, which is the total number of trials we're running, so to speak. The total number of car they're pulling out on the average. So that's all that odds means. So ratio of odds in favor, wins to losses, odds against, losses to wins. So I'd already started on this, and I decided we'd do that problem. So reconstitution of probability, what I like to call it, because if we have the odds, then we don't have the same. We don't have the probability, so we got to regenerate it. But it's thankfully not too hard because we just use this right here. All right. The probability of success is A over A plus B. The probability then of failure would be, you would just put the B over A plus B. Okay. So here's a problem that I got here. The odds in favor of a mouse being eaten by a snake in the wild is 9-2. So that's odds in favor. Odds in favor. So this is A, and that's B. Okay. So what is the probability it will be eaten? So probability of eaten, which is like our success. That's why we're going to do what we're going to do. We're going to use that right up there, the A over A plus B. So then in this case, A is 9. And down here is 9 plus 2. So 9/11ths would be the probability of be eaten. And then the probability of no eat would be B over A plus B. So B was 2. So that's the only thing that's going to change. We keep the same denominator because it's still 9 plus 2. No matter which way, you could even write 2 plus 9 if you wanted to. But since addition is commutative, the order doesn't matter. 2 over 11. And you see the good thing about this is the 2 and the 9 give us 11, which if we add those together, it would be 11 over 11. Thus, eaten and not eaten is the complements of one another. It didn't ask for the probability of not being eaten, but I wanted to just show you that you could get either one here. When 2 dice are rolled, the odds in favor of a sum of 9 are 1-8. Oh, this is the one from over there. We'll do it again, but just to show the procedure. I had done this one in earlier class because this is one of the ones over there recognized. And what it was, I thought I had recognized that problem about the roulette, but that's not the one that I had looked at. And the one that I had looked at recently, the one that's in my notes, is the amounts were different, the amount you bet. So that's why mine, like I said, that's what I was kind of expecting from that problem. Because if I do these problems a few times, I memorize the answer. And I feel pretty comfortable. That's why it's always a lot safer for me to stay on track of things I already know. But I like to get off some time because being spontaneous kind of translates into how do we actually do things. Because when you go to do your work, you're doing it afresh. You're not having to do something you've done before. That's why, in a way, teaching is different than learning. All right, so when 2 dice are rolled, the odds in favor getting a sum of 9 are 1-8. That's 1-8. Okay. So again, let's mark the A and the B. This is the I guess I can't make that any bigger. So this is the A. This is the A. And this is the B. So A is equal to 1. Oh, that's a darn disappearing 8. A is equal to 1. B is equal to 8. Okay. So we're creating probability. We're trying to find the probability of not getting. So I'm going to do it the way where I just, like I did up there, I don't have to do both of them if I don't want to. Just do the one that we want. All right. So the probability of no sum of 9 is equal to B over A plus B, because it's probability of not a sum of 9. So that's 8 over 1 plus 8, or 8/9. Okay. And then, so if we wanted the sum of 9, then it would be just 8 from 9 to give us 1/9. They didn't ask us for this, but just to show you, 1/9. And the 8/9 and the 1/9 would add up to 9/9, which is 1. Okay. Okay, let's move ahead to the expected value. Okay, the expected value. They give you this as a formula, but it's just kind of nebulous in my head. I never liked formulas when I studied math, but I understand the purpose of them, because you want to have something that works for every instance, and then you just fill in the variable parts and work it out. But basically, what this means is, if we have an experiment of some type, a game, whatever, and we want to find the expected value, then we take that thing that will happen, that we will receive, that's what the x sub 1 is, times the probability of that happening. And then we do that for each one of the possible outcomes. It's outcome times the probability of it happening. Some may be positive, some may be negative. And then we multiply all those together and add everything up. And that gives us the expected value. So here we got a game where the player, they roll the die and they get the number of $1 for the number of dots that's on the die. Well, what would be the expected value of this game? Well, for the 1, the 2, the 3, the 4, the 5, and the 6, there's 6 different outcomes. What we would get is $1, and that probability is 1/6. That probability is the same for each one of the individual outcomes, but for $2, 1/6, $3, 1/6. We multiply this across, and they don't have everything in here, but let me show you real quick. Because this is what we're going to be doing on all of these, and this is why that fraction stays the same there. And again, this is what I had talked about earlier. When you multiply times the whole number multiplies the numerator only because the denominator is 1. So 1 plus 2 plus 3. So there's 6. There's 4 more is 10, 15, and another 6. And that's where the 21/6 comes from. Leave the denominators there. Because in theory, you could simplify each one of these. Because here you would have 1/3, 1/2, and so forth. And then when you try to add them, they're all going to have a different denominator. So you'd have to go back to where you're at. So when you're multiplying, when you're adding, you do that multiplication beforehand. Make sure you don't simplify them. Because when you're adding fractions, it would just be double work to simplify them and then go back. So don't simplify your fractions when you're going to have to add them. So that's just a basic example of what. Oh, and then 21 divided by 6 is $3, 3.5. And since this represented dollars, $3.50 would be the outcome of playing this. And of course, if the outcome is, if the expected value is $3.50, every time you play, you're not going to have too many people running a game like that because they're not want to throw out $3.50 for each roll. You're going to have some in there that are losers for it to be a realistic game. All right. So raffle tickets are sold for $5 each. And this is what I was missing about that one this morning about the roulette wheel. You're paying $5 to play the game. And I should have just took it at that rather than thinking that you were winning $10. But the $10 you get back is partially your $5. So that was the mistake on that one. All right. So raffle tickets are sold for $5 each. 4 of the tickets will win prizes of 1,000, 500, 200, and $100 cash. Find the expected value if 2,000 tickets are sold. All right, so let's see. We're going to put here. This would be so this is going to be our outcome, what happens, and this is going to be our probability, and each one of the columns will be the different ones. So I'm going to write up here for the first one, $1,000, and that's more just a title because what's going to happen is our outcome is not $1,000. What is our outcome or our net winnings if we have to pay $5 for the ticket. 1,000 minus 5 is 995. So there's our net winning. There's our outcome, or X. Okay. The next one here would be the 500. Let me go ahead and just put all these in here on a minute. All right. So what's our outcome then for this one? It's 450, right? Oh, I'm sorry, 495. And with this one, it'd be 195. And then here, just 95. Okay, there's our outcome. That's what we receive net if we win the $1,000. Because we've already paid $5 to play. Now, the probability of this happening is there's only one ticket. There's one in your homework that I worked this morning, and there was like $1,000 prize, five $500 prizes, 510, and so forth. So they're all set up a little different. So you got to watch the deal. Only one 500. So each one of these is going to be 1 over 2,000. All right. What's the last option? Nothing. Nothing. No winning. Get nothing out of it. The only thing you get out of it is what?
-5. Yeah.
Yeah, losing $5. How many winning tickets are there? 1, 2, 3, 4 out of 2,000. So what we need now is the probability of that nada. 2,000 minus 4 is 1996. Let's double check it here. 2,000 minus the 4 winning tickets. So 1,996 losing tickets. I'm sorry, it was 2,000. I said it, and then I didn't write it. So out of those 2,000 tickets, there are 1,996 losers. All right. So then right here for our expected value, this is just an intermediate step. As we're going to multiply the 995 times the 1 over 2,000.
It's
And
one
remember,
thousand
that's 995 over 1.
1,995.
What's that?
It's 1,995.
Oh, for which one?
That one, 1,000 minus the $5.
$995, right?
Oh yeah. I don't know what I'm
Okay.
thinking. I'm thinking about the
I
2,000.
Yeah. Well, you're thinking like me. Like I said, I'll see something and I'll look at the wrong thing, and that's why learning is different than teaching, because with teaching I'm trying to give a flawless presentation, but learning is a whole different process, and I got to do that too. Like I'm going through and learning this Newton system, and they've got problems in there, or they've got topics in there. Well, we don't generally cover that, but I couldn't find a way to take them out, so we got to go over them. So at the end, they got these two things called um, risk ratio and odds ratio. Real easy. It's basically just like but we'll see. It's just I wanted to make sure because it kind of threw me for a loop. But once I bared down, I got it. So this is now 495 over 1 times the 1 over 2,000. Now, the good thing about this is I've kept that same denominator. I couldn't really simplify any of them other than the last one, the one for the $5 negative. I, I'm already giving the answer away. I was putting in this as an intermediate step. And then this is 95 over 1. And then negative 5. So as I said, is if you can skip this step, don't feel, and do it accurately. There's nothing wrong with that. But I just wanted to show because some people haven't done fractions in a long time, and if I hadn't done them in a long time, I have to brush up on them. I mean, it's just the way it works. I mean, uh, nobody does that stuff all the time. That's why people have jobs to do it. All right, so this right here is just going to be now what we would get. So then this is our expected value. We're going to add all these up. All right. So this is fraction 1 is, I'm going to have to get moving here. I don't want to have to rush through that. Those other things that I got. The newer stuff, this stuff. Because otherwise this would probably be the last thing I would look at right here is this. Maybe I'd do another problem. So I'm usually having to stretch this out. So they all have the same denominator, and I've kept it that way because that will make it easy. And I'm going to have to use the calculator to get that negative one because it's 5 times 1996. $9,980. All right. So let's add up all the positive ones real quick. Y'all do it as well. All right. So that means I'm just going to add up the 4 positive ones, the 995 plus the 495 plus the 195 plus the 95, and that gives us 1,780. That's the positive ones now, right? So 1,780 minus the 9,980 all over the 2,000. Okay. So I'm going to divide this by the 2,000. Whoop. Oh, wait a minute. So 1,780, it's minus the, not divided. There we go. So then this is negative 8,200 over 2,000. Okay. So what is that? Negative $4.10. So every one of the tickets nets them $4.10 the house. So everybody is essentially paying $4.10 to play on the average. But this is how they can figure out this successful game, by doing these kind of computations. Because if you offer a game that results in you losing money, then there's no incentive to play it. Now, if you want to do it for for humanity's sake, then all the better. But all right, so it's tedious. But any last questions about that? All right. So sometimes these expected values can come in different forms. In other words, you can give the expected value already, like put in in a little thing for you. This right here is what we call a probability distribution. A probability distribution, they all have to add up to 1. So the expected value of this would be this times this, this times this, this times this, this times this, and this times this. And then you would add them all up, and that would be your expected value. It's the same, we did. But what this is in there, and there's a problem like this in there. There's another one where they leave out 2. I couldn't find a way to get it out of the homework part. It won't be in the review or the um, test, but I'm going to go through one of the basic ones, because with 2, it takes too much algebra. But this is just like a little bit of algebra about like what we did on the other one. But anyway, what this amounts to, let me just write this down as an equation. Just like we did with our expected values before. Because they're giving us an expected value and they're asking us to find one of the values. Let's see what. 0. Let's see what else, but 0.2x. Right like that. How do you need parentheses for that one? So then what each one of these ends up being is, this ends up being 0 here. The next one is 0.2. The next one is, you can do it with a calculator if you like. So that ends up being 0.5, 5 times 0.1. This ends up being 10 times 0.3. It's just going to be 3. And then that one right there is the one we don't know about. We know the coefficient of 2 of 0.2x. So this was all equal to 10. All right. You know what? I'm going to do it this way to make it look like an equation. Normal, like reading it left to right. All right. So we add all these up. These end up being 3.7 because we got 3 plus 0.5 and then 0.2 more. Well, I can't hit that plus key for nothing. All right. So the step that we kind of do the algebra wise, and this is why this is, I don't want to do that second one, the one with double. So I'm just going to get rid of this. From the left side because I don't want it over there. I only want the X over there. So I'm putting my numbers on that side. So that means then right here, 0.2 or 0.2x is equal to 6.3. So 10 minus 3.1 is 6.3. I'm sorry, 3.7 gives us 6.3. And then the last step, and when I did this one in the Newton, I was kind of thinking, this can't be right when I did it. Because you come out with such a big number, but they can make anything they want. So it just looked funny when I did it. But anyway, 6.3 divided by 0.2, 31.5. So what will happen then is, if there's a 31.5 here times 0.2, then it would be what's called a valid probability distribution. You don't really need to know that now, but all of, because all of the probabilities there, see 0.2, 0.2, 0.1, so that's 0.5 and 0.5. They have to add up to 1 for it to be a valid probability distribution. So it helps to know that, but you don't really need to know it because they give you the value of the expected value in its place, and this asks you to find out what that is. All right.
Wait, what was the it was like X5. What's the 5 got to do with anything? Is it a 5?
We're at,
Yeah, so you
oh, it's just the same as the 1, 2, 3, 4, 5, the
oh, okay.
fifth act. I don't know why they did that. They should have just put
Okay.
an X there. People like to use funny variables sometimes. That's, because technically the first one would be x to the x sub 1, x sub 2, x sub 3, and so
Okay,
forth.
yeah, that was like the formula that they give you.
Yeah, I mean that's what it is. I mean, usually they'll use like up here they might put x to the I, and then so it changes depending on what x is. So then it would be 1, 2, 3, 4. But that's not that big a deal. That's why when we were doing the algebra before, and he had p, p to the a, I just change it to x just to make it simpler.
Okay, that makes sense.
All right, so these are the ones that gave me a headache last night. I had to get up early. But again, it's
So
really
I'm in
just
that right
doing,
now too.
yeah, it's really just giving the, you're doing a proportion twice. See if we can make this a little bit bigger. Okay, researchers wanted to study if wearing cotton clothes is related to depression. All right. They surveyed a large group of people. The data are shown in this contingency table. What is the relative risk of being depressed for those who wear cotton clothes? All right. Now, the key to this is those who wear cotton. All right. We're comparing cotton in both cases. Now, for relative risk, we're comparing probabilities. All right. Relative risk is taking the proportion of two probabilities. Okay. And we'll see down here, this one is odds. Because remember, probability and odds are slightly different. In a sense, it's always the same numerator, and then the denominator changes if you think of them as both fractions. But anyway, so what we're doing is we're taking depressed against not cotton. So does cotton make a difference? I mean, I'm sorry, does cotton or not cotton make a difference? All right. So we want the probabilities. So what we're using then is these denominators, the total of cotton and not common. So then what we got is we got 122, 311, and then the proportion we're comparing it to, we're creating a double proportion, 420, 683. All right. So what this ends up being, essentially, when you divide one fraction by another, you end up multiplying by the reciprocal. And then when you do it, and this is why when you do it with probabilities, like in the same scenario, they have the same denominator. The denominators leave, and you just have the numerators. But this is one step beyond that, I guess you would say. Yeah, and then this is the 420. So this comes out to, I'm just going to do it on the calculator. I'm not going to do any more there, just for the sake of time. All right, so I'm going to do 683 divided by 420. So that's going to get stuffed into the memory, and I'm going to divide again in a minute. I'm sorry, I'm going to multiply. So now 122 divided by 311 times the memory recall. So then this is 0.64. I think that's what they asked for, was round it to 2. So you're just basically dividing twice. You're making your probability for cotton versus not in cotton, because you want to find out if cotton makes a difference. And as I understand it, if that number is 1, there's no effect. If it's lower than 1, that means it's even worse than no effect. And then as the higher the number it gets, uh, let's just say it was 2.64, then that would be you basically be looking at 264% change. So just, they don't ask you all that, but they do mention it in there. They don't ask you that question, they just ask you to calculate it. And then the odds risk is slightly different. Rather than probabilities now, we're going to do it as odds. And for the sake, and this is why it's so hard to I guess you'd say the hardest part about it is odds and probabilities can be both be looked at as a ratio, as a fraction, but generally I like to write the odds as with the colon just to separate them, just so we know just to kind of make a distinction between them. But it's really the same procedure now, except that we're going to use an odd in each one of the place. So we're not going to use the total. We're going to use the number that makes up the other number that makes up the total. All right. So this one was researchers wanted to study if having a long beak is related to flying in birds. They they surveyed a total of 34 birds. The data is shown in the contingency table below. What is the odds ratio for birds that fly having long beaks against birds that do not fly long beaks? So we're measuring fly, do not fly, long beaks. All right. So this is basically just beaks versus no beaks. Or let's say versus, we can beaks to no beaks. I guess we could put the colon instead. So beaks to no beaks. There are 11 beaks there in the fly, and then not a long beak, 7. So remember, that is a ratio. I mean, that is an odd, in other words. Okay. But I'm writing it like that because we gotta divide them in order to do the proportion. That's what that means. So then on this side, it's 3 long beak to 13 not a long beak. So then our final calculation is essentially 11 sevenths over 3 thirteenths. And then when we divide, we multiply by the reciprocal. So this ends up being, I'm just going to do it with a calculator. Oh, you know what? I could just go ahead and do that. Yeah. Make it one more step with the fraction. I was going to do it as a decimal immediately. So that's 143. And 7 times 3 is 21. So 6.81. I don't know. I can't remember for sure, but I think the higher the number is, that means that there's more likely a relationship. They don't ask you about that though.
It says more
As
likely
I
in the first group slash numerator if it's greater. What does that mean? Like more likely in the numerator, basically. That's the notes that I took from it.
yeah. So the numerator then is the beak people have more propensity for flying. I thought that I read though that in the explanation it said that the beaks didn't make a difference, but that was the result. But anyway, I'm just worried about the math behind it. I'm not. We're not getting into the philosophy of it because they don't have any questions like that in there. They do explain it, but it's always just the calculation that you have to do. All right, boy, I'm done. I'm gonna be glad when this week is over with. This is like a lot of stuff. Like I said, there's a lot of stuff in this that's different and that I couldn't really take out. So if you got any questions, I'm here. Otherwise, I'll see you tomorrow. And as what I'll just tell you, and I'll tell you in the morning. I think what I'm going to do is